This video covers the first part of our notes for Unit 3 in Pre-Calculus on inverse relationships. First, let's review what exponential functions are. Each of the tables listed here represent exponential relationships. If we look at describing the pattern for what's going on, we want to see what happens to the y values as we change the x values. So for this first one, f of x here, we can see that as our x values increase by 1, so all of these x values are increasing by 1 every single time, the y values are being multiplied by 3. So the y values have what we call a common ratio. And as long as the outputs have a common ratio, we're dealing with an exponential function. So the first step, again, is describing the pattern. Once we know what the pattern is, that can help us write an equation. Our equation will be in the form of y equals, or we could write f of x equals. We'll take whatever that common ratio is, in this case 3, as the base of our exponential, and then the input value, the x, is in the exponent, hence the name exponential functions. This often won't describe the entire relationship between the two variables, so we often need to take a look at what we call the initial value in order to make the equation complete. So the initial value is what we have when our x value is 0. So if we think of initial as like the start, kind of when this function started at 0, its y value was 18. That is going to go out in front here in our equation. And if you think about testing some ordered pairs, we'll see that our equation will give us the appropriate outputs for each input. For example, if we plug into this equation that we just wrote an x value of 0, our equation would say 18 times 3 to the 0 power. Since 3 to the 0 power is 1, and 1 times 18 is 18, it gives us an output of 18. Similarly, if we were to say plug in -1 for our x value, 3 to the -1 is 1/3. 18 times 1/3 is 6, so we get our output. So that value out in front, again, the initial value, it's the output when x equals 0. The next thing we want to do for this function is talk about the end behavior. So end behavior in general means what happens to this function as our x values approach the end, kind of like really, really small values or really, really large values. And by really, really small values, I mean as x approaches like -infinity. So this notation that I'm writing down here, LIM stands for limit. Underneath it, I'm writing x with an arrow -infinity. So this is saying the limit as x approaches -infinity. We want to know what happens to the f of x values, the y values, as that happens. So in this scenario, just start thinking about what happens as our x values get smaller and smaller. We're kind of moving backwards on the table now. And if we look at what happens when we go from 162 to 54 to 18 to 6 to 2, thinking backwards, it's like we're dividing by 3. So if we were to fill in an x value of -3, our y value would be 2/3 because we're dividing. Divide again, we'll get 2/9, and we'll continue to get smaller and smaller values, never negative values because we'd be continuing to just divide by 3, but those values will approach 0 as we continue to have x values that are really, really small. So this expression here that I've written, again, the limit as x approaches -infinity of f of x equals 0, that gives me the left end behavior of the graph because the negative values fall on the left side of the graph. End behavior in general will address the left side and the right side of the graph. So similarly, we're going to write a limit expression. What happens as x gets really, really big, as x approaches infinity? What is happening to our f of x values? And this one's probably a little bit easier for you to think about. As we plug in really, really large numbers into x here in our equation, 3 to the x becomes a really large number, and then we multiply that by 18, making it even larger. If you think about the table, continuing to multiply by 3 over and over and over again for subsequent x values will produce really large numbers. So we say that the limit as x approaches infinity of f of x is infinity, because those numbers are going to get so big. So our next example over here at g of x is going to work really similarly. When we look at this pattern, we see that the y values are decreasing. We want to still think of them in terms of multiplication, because that's what an exponential function does. And so when we look from here to here, again, our x values are increasing by 1, but now our y values are being multiplied by 1/2. You may have looked at it at first and said divide by 2, but we know that multiplying by 1/2 is the same thing. So in terms of writing our equation, remember we're going to start with our initial value where x is 0. That goes out front here, so y equals 3 at that point. The base of our exponential is the common ratio, whatever we multiply subsequent y values by, and then our exponent is our x value. Plug in a couple points and you'll see that this equation holds true. In terms of these end behaviors, it's kind of the opposite of what we had before. Now we're talking about g of x. As we kind of move backwards on our table, start thinking about what happened when x is -3 and -4 and -5, we're thinking about the inverse of this relationship, so we're really multiplying by 2. These numbers in the negative x direction are going to get bigger and bigger and bigger. So the limit as x approaches negative infinity of g of x, those values are getting bigger, so the limit is infinity. Whereas the limit as x approaches positive infinity of g of x, these are going to get closer and closer and closer to 0. For the same reason, the left-hand end behavior over here got close to 0. Now that's happening on the right side here. Because we'll continue to cut these values in half over and over again, they're going to get closer and closer to 0. So to quickly recap, our general formula for exponential, this should say functions, and I believe it says that on your notes. It's just not updated on my PowerPoint. The general formula for exponential functions looks like this. Y, or again we could use f of x or g of x. Y equals a times b to the x power, where a is the initial value, where x equals 0, and b is the common ratio, what's happening to the y values from one to the next. So I've rewritten the general form of an exponential function at the top here for reference. You already have it on your paper, right above where you will see these two charts. So when we looked at f of x and g of x a couple slides ago, right at the top of your page in your notes there, one of these was an exponential growth function, one was an exponential decay function. So you might be given a table and asked to identify if it's growth or decay. You might be given a graph, and I have representations of those graphs down here, or you might be given the equation. Here's how you would identify whether it's growth or decay from the equation. We really just need to focus on the base here of the exponential. If that base is a number greater than 1, then it's going to be exponential growth, much like f of x on your paper above. For exponential decay, the base will be a value between 0 and 1, like g of x, which had the base of 1/2. We won't talk about negative bases in this regard. So for exponential functions, the base always needs to be a positive number. The next thing we want to talk about are asymptotes. We talked about end behaviors already, and we've kind of hinted at the asymptotes when we looked at those limit expressions before. So we have an asymptote for both of these functions in their parent form, as long as they're not shifted, on the x-axis. So at the line y equals 0. The domain for these functions, whether it's growth or decay, will be all real numbers, and we'll do a little bit of interval notation in this unit. So all real numbers in interval notation, we say, goes from negative infinity to infinity. Whereas the range is a little bit more restricted. We don't get negative values, again, in the parent function for these types of graphs. They sit above 0, and while it looks like they hit 0, they don't exactly, which is why we have the curved brackets here, not the square ones, because the values themselves never actually become 0, even if it looks like it. And then lastly, we need to squeeze in our end behaviors here. I don't know that I'm going to have much room, so I'm going to kind of write them over on the side. So for our exponential growth, the limit as x approaches negative infinity of some function. Well, remember, we're talking about what's happening over here as our x values are becoming more and more negative. That's approaching 0, whereas the limit as x approaches positive infinity for an exponential growth function goes to infinity. In that case, we're talking about what's happening here, and you can see that the function is going to continue to shoot on up. For the decay functions, those kind of flip-flop, again, because of the shape of the graph. So as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y will approach 0. So now that we've reviewed the basics of how exponential functions, graphs, and equations work, let's look at a couple application problems. So this first one, we have an initial value of a bank account growing at 0.59% a year is $1,500. So this $1,500 is the initial value. So remember, that's going to be at like time of 0. Initial values are when x equals 0. We need to first take this percentage and turn it into a decimal. It looks like it's already a decimal, but we know like 50% can be written as 0.5 by moving the decimal over 2 places. We're going to do the same thing here. So we want to re-express this as 0.0059 in its purely decimal form. Okay, so first part, write a model for the value of the account after t years. So I'm going to call the function v of t for the value after t years. My initial value comes first. The rate at which the account is changing goes inside these parentheses. Now, I'm still going to have that $1,500 to start, and I'm getting this extra 0.0059 on top of that. So the rate, because it's going to grow, needs to be greater than 1. I'm going to add that percentage to 1 and make my exponent my input variable, so after t years. So again, initial value here, the rate added on top of 100% of what we would have because this is going to be growing. Next, to find the value of the account after 30 years, we simply plug 30 in for time. You'd get out your calculators to see what this gives us when we put 30 in as our exponent. you should see that it's about $1,789.52. And then 3 is really asking us for an end behavior. It says if the money is left in the account forever, so think of this as our time approaches infinity, what is the long-term behavior of the account? So the limit of our function, as t gets really big, well, it's going to just continue to grow, right? So it's going to approach infinity dollars, which sounds pretty good. This next problem is a common problem to come up in, say, a chemistry class. It's talking about half-life. Half-life of a radioactive substance is 30 days. That means it takes 30 days for the substance itself to be halved, to cut in half. Initially, there is 10 grams, so that's going to be important. We want to write an equation for the amount of the substance remaining as a function of time. So let's get started on a few pieces here. Let's use function notation. So a function of time. We know our initial value is 10 grams. And our base is going to be 1/2 because it's talking about half-life. We know that t needs to show up in our exponent. But we need to do a little adjusting here. The half-life is 30 days. So that means when we plug 30 in for time, we need to have half of the initial value, half of the 10 left over. So let's think about this over here on how we can adjust the time. So remember, we want to get 5 out of our equation. We're starting with 10. Our base is 1/2, and we need to plug 30 in for t. Now, obviously, 10 times 1/2 to the 30 power isn't going to be 5. In order to get this to be 5 over here, we really need this exponent of 30 to be a 1, because 10 times 1/2 is what gives us 5. So the adjustment that we need to make is to divide that 30 by 30 so that we get 1 in our exponent, and we get 5 on either side. So we just need to come back over here and apply that to our equation. Divide this t by the time it takes for it to be halved, and then this is our final function for the half-life of the substance. So initial value, half-life, and then adjust for the time it takes to get that half. Our last two examples might feel a little more similar to example A, and then C and D are certainly related to one another. So we're going to continue to talk about growth and decay in part C here in terms of the number of bacteria in a petri dish after some time t. And we want to know the initial population and also if the colony is growing or decaying. This first part is pretty straightforward. So remember, the initial population is this value out in front here. I just want to reiterate that that's what happens when t equals 0. So if we were to actually plug in 0, our exponent becomes 0 altogether. E to the 0 is 1, and we get 100 out. So I know that's quite a process to go through, but I just kind of want to reiterate that that's what we mean by initial when we plug in 0. Certainly you could have seen that from the formula here. Now, in terms of knowing whether the colony is growing or decaying, we have to know what the base is, and the base is kind of hidden here. We can see this e to some power, and then the t is tacked on to that power at the end. We have to figure out what e to the 0.693 is equal to before we can determine what the base actually is. So you have the E button on your calculator. E is a number, it's approximately 2.7. It's the second function over your ln button, which is the natural log. So I need you to locate that button, type in e to the 0.693 power, and you should get approximately 1.9997. That means this function could be rewritten as 100 times about 1.9997 all to the t power, where then our exponent is just that variable t. This makes it easier to tell whether the colony is growing or decaying. We can see that the 1.9997 is the base, which is greater than 1. Therefore, the colony is growing. In order to find the rate, we don't just name the rate as the base. The rate is the difference from 1. So the rate will be equal to 1.997 minus 1. So it's growing at a rate of 0.9997, also known as 99.97%. So our last example today, again, similar to part C. You can see we're talking about a similar kind of equation where we have our base written as this e to some power number. So knowing we're going to have to deal with that, let's go ahead and type that into our calculators and figure out another way to represent this equation so that we can, sorry, you don't want the t on there, so that we can more easily answer these questions. If you type this into your calculator, I believe you should get 0.9672, which means the entire function could be rewritten as such. And now that we can see that 0.9672 is less than 1, we know that the population of Detroit is unfortunately decaying. So it's getting smaller. In terms of answering the question, at what rate, I can't emphasize enough that in order to find the rate, we don't just name the base. It's the difference from 1, because we're seeing really what's its difference from 100%. So take the base of 0.9672, subtract that from 1, it is decaying at a rate of 0.0328, which we would say about 3.28%. So the population is decaying at about 3.28% per year. Lastly, if this rate continues, what size will the population approach in the long run? So this is another end behavior kind of question. So what is going to happen in the long run as t gets bigger and bigger and bigger as it approaches infinity of our population model for Detroit? And because it's decaying, eventually, if it continued, there wouldn't be anybody left. In the long run, we would have 0 people. Hopefully this also kind of helps you think about why we don't talk about negative values in terms of the exponentials. That wraps up this section of the notes. We'll see you next time.